Hello, everyone, welcome to the presentation of our recent work on CVPR2023. This work introduces a general framework called MMANet to assist incomplete multimodal learning. For a multimodal task, while a variety of sensory modalities can be collected for training, not all of them are always available in practical scenarios due to the limitation of device and work conditions. This raises the challenge to infer with incomplete modality. Therefore, we need to learn a multimodal model that is robust to random modality missing at inference. To address this problem, many methods have been proposed and can be roughly categorized into two types: customized methods and unified. Customized methods aim to train a specific model to recover the missing modality in each incomplete modality combination. This is complex in practical applications. Therefore, the unified methods are proposed to train one model to deal with different modality combinations by extracting the modality invariant features. Besides, since multimodal models tend to fit the discriminative modality combination and result in worse performance for weak ones, existing unified methods introduce the auxiliary discriminator to balance the training. While existing methods achieve promising results, they still suffer two limitations. Firstly, they only consider the modality invariant information while ignoring the modality-specific information. As a result, they usually perform much worse than the customized methods. Besides, they hypothesize that multimodal input is more discriminative than unimodal one. However, it is not absolutely true when more than two modalities are considered. As shown in table, no matter for the customized model or the unified model, the single depth modality outperforms the RGB, IR, and their combinations. To overcome existing limitations, we propose a general framework called MMANet to assist incomplete multimodal learning. It consists of three parts: deployment network, teacher network, and regularization network. Specifically, the deployment network is the final inference network. To make it robust to the modality incompleteness, we introduce the Bernoulli indicator after modality encoders and randomly set some components of them as 0 during training. Besides, we introduce the teacher network that is pre-trained with complete multimodal data. To transfer the comprehensive multimodal knowledge to the deployment network via the MAD, enabling it to acquire the modality invariant and specific features simultaneously. Finally, we introduce the regularization network to mine weak modalities via the MAR, enabling the deployment network to balance weak modality combinations effectively. And total training loss is the sum of the three modules. Then we introduce the detail of MAD. Firstly, to overcome the input heterogeneity, MAD proposes to transfer the teacher's knowledge via relation consistency instead of feature consistency. Here, we implement it with conventional SP distillation. Besides, MAD introduces the classification uncertainty of samples to reweigh their contribution to the final loss. This encourages the unified model to pay more attention to the hard samples nearby the class boundary. Then, we introduce the detail of March. As shown in the right figure, DNNs tend to first memorize discriminative combinations before the weak ones. Therefore, MAR mines the weak combination by calculating the prediction distance between incomplete and complete combination. The weak combinations are ones containing the top k distance. Then, MAR calculates the prediction loss for the weak modality combinations individually, guiding the deployment network to pay more attention to them. Finally, we introduce the results. First, this slide shows the classification results on the KSurf dataset. As shown in the table, MMANet achieves the best performance for all combinations. Compared with the second best unified method, MMFormer, MMANet decreases the average ACER by 1.99%. This shows the superiority of our method on the incomplete multimodal classification task. More importantly, MMANet even outperforms the customized baseline method, SF, for all the modality combinations, decreasing the average ACER by 1.86% and 1.66%. This demonstrates the effectiveness of the proposed MAD and MAR for the incomplete multimodal classification task. Besides, MMANet also achieves the best performance for all the modality combinations in the segmentation task, confirming the effectiveness of the proposed MAD and MAR on the incomplete multimodal segmentation task. Then it's the ablation experiments of MAD. For both classification and segmentation tasks, MAD outperforms the conventional SP, confirming its effectiveness. Besides, we further visualized the interclass distance. confirming that MAD can encourage the deployment network to focus on the hard samples and thus acquire a more separable interclass margin than the conventional SP. MAR also outperforms the conventional single-modality regularization in both classification and segmentation tasks, confirming its effectiveness. And the performance gain of MAR mainly comes from RGB, IR, as well as the combination of RGB and IR, confirming MAR can mine the weak modality combinations more accurately and force the deployment network to improve its discrimination ability for them. Finally, in general, this work has three main contributions. A margin-aware distillation, MAD, strategy to overcome the input heterogeneity and embeds comprehensive multimodal information to the deployment network. A modality-aware regularizer, MAR, to mine and regularize the weak modality adaptively. And a model and task-agnostic framework MMANet to assist incomplete multimodal learning via MAD and MARCH. The code of the paper can be get in the given URL.